Welcome in this video where we are going to implement a great math paper. That's a very nice paper related to normalizing flows onto generative AI. And it was written by three awesome researchers. The first author, George Papamacarios, is now a research scientist at Google DeepMind. He was in the Gemini team. Well, I believe he still is in the Gemini team. With the second author, that is a researcher. I'm not sure about the title, but he is now at Google. On Ian Murray, to the best of my knowledge, is still a professor at the University of Edinburgh. Okay, so as always, we are going to re-implement the paper in a self-contained way. Everything will be in a single Python file, self-contained, not using any other libraries. I mean, for the flow implementation, we are going to implement everything from scratch. We are just going to rely on PyTorch for automatic differentiation. These are the results you can expect by the end of this video. So I believe these are pretty nice looking results on the MNIST data. So yeah, let's dive in directly. We're going to use PyTorch, as I said. We're going to use Keras for just loading the data so that you don't need to manually download the data or unload them. Yeah, so let's dive in. The math paper relies on the MADE architecture for implementing the autoregressive, to have an autoregressive model in an efficient way that do not require sequential iterations. We are going to come back to that later. So basically here what we take into in input, it's a 1D tensor of in degrees. Okay, so basically let's say you have values in that, 0, 1, 2, 3, on out degrees, a tensor of the same shape with degrees like 1, 2, 3 as well. And basically this returns a mask that basically connects in degree to outer degree only if they have the same degrees. Okay, so we create the mask, then we can because it's normalizing flow and because we use the change of variable formula, we need to compute the density of the data p of x. We need the on one side we need the Jacobian, on the other side we need the density of the latent dimension associated to the data, because it's a bijective transformation. So to every x we map one variable z, and we need to be able to compute the density of z. Okay, I believe you are already familiar with that. In my latest video I made a paper review, so I will not spend too much time on the maths. I'm just going to focus on the implementation. But basically, yeah, to implement equation 7, the change of variable theorem, we need to be able to compute the density of the latent. Okay, we need to be able to compute p of z. That is what this is doing. Okay, then this paper is using batch normalization, so we can implement batch normalization with the beta and gamma parameters that are learned parameters, and then there is the mean and the variance. During training, we compute, we are going to track the mean and the variance. Well, as opposed to standard batch normalization, here we are not going to track the mean and the variance. We are going to use the batch statistics during training. And then what we will do at inference, well, after training, we are going to run the full pass on the full training data, and we are going to do what we call a calibration. We are going to calibrate the mean and the variance on the full data set after training. Okay. Yeah, that's one way to do basically to fit the mean and the variance for batch normalization. The most standard way is just to track the mean and the variance during training with an exponential moving average. Here, this approach with the calibration is also used a lot in for working with a covariate shift or out of distributions inference. So basically, when you have a shift, when there is a shift between your training and your testing distribution, yeah, calibrating the parameters of the batch norm with different techniques allow to solve those kind of issues with covariate shift. Okay, but coming back to this, so basically we are going maybe to come back to that when we have the full code implemented. But basically here you see we have a begin calibration function to say we are starting the calibration, end calibration function to say we are ending the calibration. And now maybe if we come back to all of that, so basically what we'll do when we begin the calibration, we reinitialize those temporary variables. Okay, we track the sum, okay, of the features. Well, maybe let's move further to check what is sum of squares on count. But basically here we compute the batch statistics. This will be used during training. When we are training, we're using the mean and the variance of the data X. So we're going to call compute batch statistics. So okay, and now we're coming in the fourth pass. On here we have the flag if self.collecting. On we will so now we can have a deeper look at the calibration. So when we are done with training, we're going to call this function to say, okay, we're beginning the calibration. We're going to run the model on all the training data. So basically here we're going to accumulate the sum of the data X, the sum of the square, okay? And we're going to compute how many elements we have in X, okay? So by the end, when we run that with batches on the full data, at the end we have the sum of X. So X are always the input to the batch normalization. So in a way, the hidden features are different after different layers. So basically, yeah, we have those sum of the hidden features, the sum of the squares on count. And basically, based on those variables, at the end of the calibration, we can compute the mean. So the mean is a combination of the sum of the number of elements. We can also compute the variance using the sum of squares on the mean that we've just computed. So basically, yeah, after training, we run this calibration pass, and then we get the mean and the variance, and we use those values for inference, okay? Again, that's used a lot in some domains, such as out of distribution inference or coverage shift. But here in this paper, this is also what they use. Okay, so basically that was at the end of training, if we were collecting statistics. Otherwise, if we're just training, again, we just use the mean and the variance from the batch. And if we're doing inference, we use the mean and the variance that have been computed during calibration, okay, line 47 and 48. Okay, so now we can basically just run the full pass. So we compute the output of the batch normalization, and because it is a normalizing flow, we need to track the log determinant so that we can use it in the change of variable formula, so that we can compute P of X and train the model with total by maximizing the total log marginal likelihood of the training data. So yeah, we track the log determinant of the Jacobian. Okay, and if we want to go from data space to latent space, but if I want to sample for my model, I want to go from latent space to data space, and I need to be able to invert this transformation, and that's what we implement in the inverse function. Okay, so we've implemented the batch normalization. That was not the most important part of the MAF paper. What we're interested in is really the MAF thing. But I think this batch normalization, it's really great to know the details of that, and also to know how you can calibrate the mean and the variance. The standard way is just with running means and running variance. That's the default behavior in PyTorch. But this is in some ML application, this is really critical, so it's good to know. Okay, let's move on to the mask linear. One principal component of MADE, the basics of MADE. Basically, it's very easy to implement. Basically, we just we create a wrapper on top of the linear class in PyTorch, and basically we're just going to mask the weight with a mask, so that our output I, well, it depends on what is in our mask, but if our mask is created using this function, create mask, that means that the output 1, the first output of the neural network, will only depend on the first input. On the second output of the neural network will also only depend on the first two inputs, and so on and so forth. And basically, we discussed that last week or on Wednesday during the paper review. But that allows to have to compute basically equation 2. Okay, basically we can decompose the maybe it's a bit above. We can decompose the joint density P of X into a product of one-dimensional conditionals. But even if we don't do that, basically we are just making sure that the neural network is autoregressive. That the output at index I is only dependent on the input at index I minus 1. And again, we do that in a single fold pass. With that implementation, it's only 4 lines of code. Okay, so now we can create the MADE architecture. Basically, it's just basically just a wrapper on top of the mask linear, or maybe it's calling the mask linear properly. So basically we take as input the features in our made layer. The number of input features, the number of hidden features, and the number of hidden layers. So basically it will be a combination of different mask layers. So basically what we do, so basically we're going to order all the, we're going to assign an index to all units. So basically for my input layer, I'm assigning degrees from 1 to D. Then for my, I do the same for each hidden unit. Okay, I'm numbering the units from 1 to D. Okay, here I believe it should be D as well. On here D as well. I'm not sure why it's D minus 1. Yeah, so basically, and then we also do that for the output layer. Here we do ordering minus 1. So basically here it will go from 0 to D minus 1. Why? Because here we have lower or equal, okay? So basically I want that my input, that my output at index I only uses the input at index I minus 1, okay? So basically that's why I do this minus 1, because I don't want, otherwise, because here I have a smaller or equal, output at index I will depend on inputs at index I or lower, and we want I minus 1, okay? If here I had used a strictly smaller, that will not be needed, this minus 1. I just need to be consistent with my code. Okay, and then basically once I've created my my ordering, my degrees, basically I can call my mask linear, basically I'm creating a sequence of mask linear layers. This is the first one. This is the input linear layer, and we feed it the mask that we create based on the based on those orderings that we've created. Okay, and I'm adding a ReLU at the end. That's for the input layer. Then we can add the hidden layers into the model, and finally we can add the output layer. Okay, here for the output we have twice more features. It's because for the output we need to predict the mean on the log standard deviation. Okay, we are modeling what our neural network is modeling. We are modeling the mean on the log standard deviation. So what I could do is described in this equation 2. I could have one neural network that outputs the mean, one neural network that outputs the standard deviation, but here we've decided to combine everything in a single neural network. So it's as if the beginning of the neural network was shared, and then at the end there are two branches, one that computes the mean, one that computes the standard deviation. So in a way we have a neural network, or two neural networks with shared parameters. We could also have decided just to implement them separately. Okay, and then the fourth pass, so basically we compute the mean on the log standard deviation. Basically the rightmost side here of equation 2, and then we can use equation 3, the reparameterization trick, to sample from this distribution. But for now we're just predicting. Oh no, let me check. Okay, we are computing z from y minus shift. Okay, so basically we implement equation 4. Okay, so we compute the transformation. We also compute its the log Jacobian. Okay, that's equation 5. So very easy to compute because of the nature of the architecture. By design, it is autoregressive, so the Jacobian is slower triangular, and therefore computing the log determinant of the Jacobian is very easy. Okay, so now we can implement the inverse. So basically, it's the opposite. Instead of going from y to z, we go from z to y. Basically, this is a very simple equation, very simple to invert. Okay, so here what we can do, what we want to make sure is that we basically here with my index I will always be my output at index I will only depend on the previous inputs. So basically that means that if I'm always using the same order, basically that means that the first pixel, or let's say the second pixel, will only see only the first pixel, okay? Because the output, because of the made architecture, will only depend on input at lower indices. But what we want to do, we can do that without breaking the autoregressive nature. After the first layer, maybe I want to shuffle the indices so that now my, for example, here we're permuting, we're reversing the array. Maybe we can move on in the code. Yeah, basically we're permuting because you can see we start from n to 0 or n to -1, but -1 is excluded, and we decrease. So basically the permutation goes from n to 0, well, n -1 to 0. So basically here what we do, in between every layer, we invert we flip the image in a way. That's as if here, instead of having degrees in 1 to D, we had degrees in D to 1. So that, for example, in the very first layer, your output at index 2 is only dependent on the input at index 1. But then at the second layer, the output at index 2 is dependent on all the other values except the first one, okay? You are always in between layers inverting the permutation. Very likely it's better explained in the paper than my explanation at the moment. Yeah. Okay. Maybe I don't want to go too much into details, but basically here, 95, what we did some, instead of just doing some torch arrange to have degrees going from 1 to D, instead we are shuffling them, okay? So because of this shuffling, this reverse permutation might not be needed, or actually it's not needed, but actually yeah, this adds a bit of randomness, a bit of robustness. If you want to be too strictly for the paper, you can say torch.arrange, and then this is strictly needed. But if you keep this torch.runs in, you are already shuffling the indices, and this could be removed. Okay, well, now that we have our building blocks, we can create the MAF architecture. Yeah, basically we're going to combine our made with batch normalization. The batch normalization is between each made layer. And therefore, that's why we need to be able to compute the log determinant of the batch norm, because what we want to do is to compute the log determinant. Here, equation 8, we want to compute p of x, or p of x. We want to compute p of x for the full transformation, and therefore the batch norm, we need to be able to compute the log determinant of the batch norm. For example, here the neural networks, fu, so basically the mask linear layer. Here, that's equation 2 or 3, f of u and f of alpha. They can be as complex as we want. For those neural networks, we don't need, as opposed to some normalizing flow architecture, there are absolutely no constraints on f of u and f of a. They can be as complex as needed, and we don't need to compute the Jacobian, okay? So basically, if I had used a batch normalization in f of u and f of alpha, then there is no need to compute the log determinant. But because here I'm using it in between made blocks, I'm using it in my MAF class, I need to be able to compute the Jacobian in an efficient way, okay? On what we do, yeah, in between every layer, we do a reverse permutation, except for the last layer, and that's explained in the paper as well. Okay, and then the MAF forward pass, it's very easy. We just go from one layer to the other. We accumulate the log Jacobian, and yeah, we transform the output little by little. And we can do the same for the invert function, but now we reverse the order of the transforms. Okay, we can create two functions. So for this MAF architecture, for this MAF class, we can have a function begin calibration. So basically, it will iterate to all blocks in this architecture. And if the block is a batch norm, we're going to call the begin calibration function on the batch norm layer. We're going to do the same with the end calibration function. Yeah, and then we should be done with the MAF class. We can move on. So what is really important with normalizing flows, it's dequantization of the data. Because data are discrete, they go from 0 to 255. What we do, we transform the data, we divide them by 255. So values are between 0 and 1, but they are still discrete, right? They are between 0 and 1, but there are only 255 values in the tensor. Well, there are only 255 possible values. So what we do dequantization, we add a bit of noise. We will do that later in the training loop. And for normalizing flows, it's very important. Because otherwise, we try to do this bijective mapping between a distribution with low entropy to a distribution with high entropy, and that makes training very difficult. So what we do with normalizing flows, we add some noise to dequantize the data, and usually on top of that, we add a logit transform. So basically, instead of training the data, instead of training the flows in the, let's call it data space or dequantized data space, we add a logit on top of it, and we train in that logit space. And usually that leads to easier training and better results. So basically here we just compute the logit, its determinant, its log Jacobian, the log determinant of the Jacobian, and we also implement the inverse function. Okay, now we're done. We've implemented everything we need. We can implement the main function. So we're going to train on the GPU. We can load the data from the Keras library. We can load the training data. We divide them by 255. Again, even if we do this, data are still discrete. The D type now in PyTorch is float 32, but data are still discrete. They take only 255 values. Then we create our data loader with a batch size of 100. We create the model, we create the logit class so that we can use it, and then we create the optimizer. And finally, we can start training. So we iterate for a given number of epoch. We iterate over batches in the training loader. We push the data to the device. We create some noise to the dequantization. So basically, the dequantization level, the amount of noise we add, it's random. But basically, it's the value in between 2 pixels. At most, between 2 pixels, I have 1 divided by 255. So we sample noise in that range, okay? And then when this is done with X dequant, so the dequantized value, we apply a logit on top of it. And basically we train now in that space, we train the flow on Y, on the not on X, okay? Then we can compute the log probability of the latent, and basically combine them to implement equation 8, to implement to compute P of X, and then to train the model with total log marginal likelihood maximization. Okay, we can do the gradient step, and then we can move on. So what we need to do before sampling images and before saving this kind of image, then we need to start calibration. So we start the calibration. So what we need to do, we need to feed the full dataset to the model. So basically we feed data little by little to the model, and then we can stop the calibration. And that means that now we have a mean and variance that we can use. The batch normalization have the mean and variance that will be used during inference. In some applications, for example, this is done with some inference data. The issue is that you don't know in advance what will be your data at inference. But for example, you have the applications, for example, like Google, let's say YouTube, let's say Google Google Ads, for example, they receive thousands or millions of clicks every second. So what they can do, they can use those. They can have a window of maybe 2 seconds where they collect data. Then they use those inference data to calibrate the model, and then they can use those mean and variance later. Okay, and all of that is explained well in papers on out of distribution inference or on covariate shift. Okay, and finally we can sample. Here I've sampled with a temperature of 0.7. So again, the more when you increase the temperature, or here when you decrease it, but basically the temperature allows you to have a trade-off between diversity and quality of the samples. On here you can see that with this value, you still keep you still keep diversity in your generated sample, but you get better samples. Okay, so basically we sample 25 images. We need to be careful that those images are in the logit space. So we need to go from logit space to data space. We do that by using our logit class on calling it with the reverse equal to true. And then we have 25 images, and we can finally plot them and save the image. So I really hope this video was helpful to you. If you want more videos on just machine learning or in more detail about generative AI, normalizing flows, nerve Gaussian splatting, diffusion models, subscribe. And if this video was helpful, please like it. It's really helpful for the algorithm. You can also comment, even a very basic comment. Just thank you. Yeah, thank you very much, and see you in the next video.